Thank you for giving us this opportunity to present the work that we've been doing on the ReDiCom project, which stands for Resilient Communications for First Responders in Disaster Management. We've all seen often that communication is key to managing a disaster. It is a critical component of improving outcomes and saving lives. We recognize that during disasters and after a disaster, there are many challenges to providing communications. Infrastructure that we generally depend on may be impacted. We focus on what are key aspects for providing an effective response to an incident. First responder teams are dynamically formed, comprising members from many departments. There's a need to provide a means to provide timely dissemination of information. And publish subscribe is often a good service interface for this. We first create an information layer that facilitates the communication with dynamically formed first responder teams. This uses information-centric principles to allow for role-based communication rather than being based on location or individual identities. This is done by creating a dynamically formed incident management namespace that brings people from different organizational structures together. To deal with infrastructure disruption, we support device-to-device direct communication. It allows for first responders within a partitioned environment, for example, a shelter that may be cut off from the rest of the environment, at least in terms of communication, to be able to communicate with each other, but also accommodates the occasional communication that may be available to points outside the partition, for example, using a data mule or intermittent or carefully managed satellite access. In addition to supporting D2D communication using different link layer technologies like Wi-Fi Direct, Bluetooth, and LTE Direct, and 5G direct communication using cellular networks, we also seek to use the various devices that may be in the partition, such as all the smartphones of people within the shelter, to perform complex computation tasks. Examples of these may be face recognition, text-to-speech conversion, etc., where using only a single device may be too slow. The remainder of our presentation is split into 4 parts. The first is on exploiting naming for scalable, consistent dissemination of information. Second, we will discuss routing in D2D environments with binary state DVRP. Third, we'll describe our work on coding for reliable D2D computation and communication. Finally, we'll discuss how we are integrating all of ReDiCom's capabilities together. Our namespace design goes beyond the traditional simple hierarchical namespace. We accommodate a graph structure. It allows us to have multiple dimensions for each node in the namespace. Importantly, we allow the namespace to be dynamic with nodes and edges that can be dynamically added or removed. We use this namespace as the framework for supporting a rich publish-subscribe service interface that allows for timely delivery of relevant information to the appropriate recipients. We now look at how this naming framework can be used for scalable information dissemination. We assume a disconnected, delay-tolerant networking environment with no physical clock synchronization and geographical routing. We assume users such as first responders and incident commanders are equipped with mobile devices for creating and disseminating updates. If such updates are created by many users and associated with a common shared database, the consistency of such dissemination is important, and it's especially challenging in a disconnected environment. 2 such use cases where naming comes to play are namespace propagation and an application that we think of called map-based geotagging. Our goal is to ensure that data gets delivered consistently to all relevant users throughout the infrastructureless environment. To scale information dissemination, we divide our namespace database into regions or partitions known a priori by users from a known template. Each update message in this namespace propagation is a change in nodes or edges in the namespace, and as to which partition it belongs to. As different people, including incident commanders, make changes to the same namespace graph, ensuring consistency becomes important. An important part of consistency is ensuring causality. A user's update may depend on his previous update or someone else's update on the same region. We mainly focus on the map-based geotagging application to explain our approach for consistent dissemination of information. We assume the map background layer and its region divisions are already available to all users offline. This regioning is hierarchical, as shown in this example, and are captured in a namespace graph. Dynamic updates are data in the form of pins or shapes put on the map by first responders, such as A and B associated with different regions. Here is an example scenario. We rely on opportunistic exchange between users and assume a fragmented environment. For example, users A and B are in one fragment and users C and D in another. A, C, and D are first responders and B is a civilian. A creates a pin on region R111 at time t1. Assuming user B moves according to the trajectory shown, acting as a mule, A's update is now accessible to C and D. The use of the namespace makes sure only relevant, interested users receive the update, such as C, who's dealing with region R111, and D, who's dealing with R11, which includes R111 as the namespace shows. We also need to ensure consistency when many users create many updates without central coordination. This is an architectural overview of our solution. We ensure 3 levels of consistency: replication, that is level 0, causality, which is level 1, and agreement, that is level 2. Each level has a name-based interest profile, NBIP as we call it, pointing to a subset of the namespace, capturing the relevance for each user per level. Consistency level 0 or replication makes sure users receive the created updates without regard to order. The gossiping component at the lowest layer takes care of replication, and we use and enhance epidemic routing for this component. Name-based interest profile 0 specifies which updates a user participates in for relaying purposes. All updates not matching it will be discarded and dropped by the gossiping module. Epidemic routing aims to deliver messages with high probability in delay-tolerant network environments. It uses anti-entropy sessions to relay messages using summary vectors of buffered messages. Whenever two nodes come into contact, they exchange summary vectors and consequently messages that the other node is missing. Our enhancement includes the specification of a region along with the update. Each update belongs to exactly one region, which is the smallest region large enough to contain an update on the map. And each update covers a set of regions, which are all leaf node regions it intersects with. For example, in the figure, update A belongs to R111 and covers R111, while B belongs to R12 and covers both R122 and R123. Updates are received by subscribers of its regions covered set and the regions above them in the namespace hierarchy. For example, subscribers of R1, R12, R122, and R123 will receive update B. The next consistency level, level 1, is about causality, which is to make sure users get a causally ordered view of updates captured in what we call a moderate view. It's called a moderate view because causality provides only a moderate level of consistency. In our design, the causal ordering component takes care of this, and we use and enhance vector clocks for this purpose. Name-based interest profile 1 specifies which are the updates a user participates in the causal ordering procedure. Vector clock is a popular and established method of causal ordering, building on the concept of logical clocks and the notion of causal before and after ordering. In this definition, we say that a message M1 causally precedes message M2 if one of these three conditions hold. FIFO order, meaning some user A sends M1, then he sends M2. Local order, meaning user A receives M1 and then sends M2, or transitivity, meaning there is a message M3 such that M1 precedes M3 and M3 precedes M2. There are non-blocking and blocking methods to capture the causal history of a message. For message size scalability, it is preferable to use metadata in a message, just like what vector clock does. Here is an example of vector clock for local ordering. There are three users or processes, P1, P2, and P3, each starting with all 0 local vectors. The vector contains an entry for each process. Assume P1 creates and broadcasts a message M1. M1 contains the incremented vector 1, 0, 0. P2 receives M1, sees that the carried vector is one step away from its clock, which makes P2 accept M1 and causally delivers it to its higher layers. Now P2 sends M2 with an incremented vector, indicating that M2 causally depends on M1. P1 receives M2 and accepts it since it has M1 already. P3 receives M2, but since it doesn't have M1 yet, we'll put M2 on hold. Now let's assume M1 reaches P3. After causal delivery of M1 at P3, P3 then accepts and applies M2. This is how vector clock blocks a message until all the dependencies are satisfied. Causal ordering is important in our application. A map update can depend on other updates. For example, update C may remove what update B added in the same region. We use a blocking method similar to vector clocks. Enhancing it, we use named regions to only include potentially dependent messages rather than full vectors. Each update includes the created user's ID, region belong to, region's covered set, a sequence number, and a set of references. We specify dependencies in two ways, implicit and explicit. Implicit dependency relates to the same user's update on the same region using sequence numbers for user region pairs. For example, A R1 3 precedes A R1 4, which ensures FIFO ordering. Explicit dependency relates to other users' updates on the same region using the references which identify other users' updates on the same region. For example, A R1 3 precedes B R1 1 with reference to A R1 3, thus ensuring local ordering. Because of missing dependencies, blocking an update, there may be gaps in the sequence of received messages for causal deliveries, especially due to a disconnected environment. We add a reactive mode on top of it to fill gaps rather than merely waiting for them. The next consistency level, level 2, is agreement, which is to make sure users get an agreed upon view of updates captured in the strong view. This is a stronger level of consistency than causal consistency, enabling a total order of all updates, not just the ones that can be causally ordered. Our consensus component takes care of this, for which we use and enhance the so-called one-third rule algorithm. Name-based interest profile 2 specifies which updates a user participates in for consensus sessions. Consensus is a fundamental and important procedure in distributed systems, and its goal is to achieve agreement between a group of nodes on a particular value. Here, the value to decide on is the next update to apply to the strong view across users. Classic consensus algorithms such as Paxos and Raft assume reliable links and only accommodate node failures, so they're not suitable for highly transient networks. There have been consensus algorithms proposed that tolerate loss and unreliable links. They assume asynchronous environments, but with good periods where a message is eventually reachable to any node except for nodes that have permanently crashed. There are two algorithms for such cases. These are the one-third rule and the Paxos last voting algorithm. OTR is coordinator free, while Paxos last voting needs a coordinator. Also, OTR has the potential to finish in a single round, so we pick OTR to use and enhance. Let's assume a user X is a subscriber of R1 and has causally received the updates shown, each belonging to a region at or under R1. There will be a consensus session for each update slot for a region. There are two types of messages, contribution and decision. Let's assume X sends a contribution for the first slot of region R11. The contribution message will contain X's user ID and also its vote, which is A. A round ID is also included. We add a notion of an attempt number, as in some cases we might need to redo the consensus session. Population, or N, is the number of subscribers of region R11 and above, as per user X's estimation. This is the number of participants in this consensus session, which is needed to determine a majority vote. Here, this contribution gets disseminated for subscribers of R11 and above. Users create a contribution either by initiating it or are triggered by receiving others' contributions. In the next round, users update the value to a two-third majority value and the population estimation, that is to the highest N received. A decision message is then generated. We evaluate our system with experiments on a subset of the city of Helsinki. We choose Helsinki because we had mobility data that was modeled before. Our namespace, as shown, follows a hierarchy: city, major district, district, neighborhood. Our scenarios are in the southern major district with 3 districts and is over a 4.5 by 3.4 kilometer region. We put 30 mobile first responders, 10 responsible for each of the 3 districts. We put additional benevolent mules, 500 civilians, and 50 vehicles that also help in delivery of information. They don't participate in the consensus sessions, however. Each first responder creates 3 updates. We experiment for the 3 incremental consistency levels and compare alternatives using the one simulator. First, we focus on level 0 and the impact of adding naming to epidemic routing. As the results show, our solution achieves higher replication coverage of relevant updates among first responders, leading to more relevant deliveries with better latency to first responders. We also achieve lower buffer consumption at the first responders, even with a similar number of total relays in the network. Then we bring level 1 and causal ordering into play. With use of named regioning, name-based interest profiling, and the reactive mode, our solution achieves higher causal completeness of relevant updates at first responders. We achieve more relevant causal deliveries with better latency to first responders. Also, we get lower buffer consumption at first responders with a similar number of total relays in the network. We also see that the use of the reactive mode, which obviously adds more cost, achieves better causal completeness. Finally, we focus on level 2 with agreement and consensus. With the use of naming, our solution achieves higher agreement completeness of relevant updates at first responders. We get more relevant decisions and deliveries with better decision latency at first responders. We also see the decision latencies are in the order of hours, which justifies also having a moderate view in the interim for practical reasons. Our solution also achieves lower buffer consumption at first responders, despite a similar number of total relays in the network. In summary, we designed a framework for consistent dissemination of information in intermittently connected environments for emergency response. We allow for incremental consistency levels for replication, causality, and agreement with different amounts of overhead at each level. We couple the organization of the information flow and consistency procedures using naming with region-bound publications and name-based interest profiles for better effectiveness and efficiency. By using naming, we optimize consensus and significantly increase the agreement completeness across first responders while reducing their devices' buffer usage. Next, we plan on integrating security into our naming and information dissemination framework.
For our work on the dynamic routing protocol, we consider a first responder network composed of multiple network partitions, which may include multiple shelters along with a command center. You are seeing an example with a single shelter. In this network setting, the patrol car plays the vital role of a data mule, acting as a communication relay between the shelter and the command center. We need a routing protocol that can deliver data messages between the shelter and the command center. For instance, the nodes at the shelter must have the capability to figure out that packet 6 is destined to the command center, and it must be given to the patrol car during encounter 1. Later, when the patrol car arrives back to the command center, it must figure out that destination C is located in the center and deliver the packet 6 to its destination. Such capability is not available in traditional routing, and delay or disconnection tolerant routing capability is needed. Given the characteristics of our disconnected network environment, our routing protocol aims to achieve some important design goals. We want to be able to handle underlying device-to-device links, which appear as TCP-like sockets to the network layer. This is not common in most routing designs, as they assume such links appear as UDP-like sockets, where routers directly send packets to any other router that they are connected with, without the need for establishing a connection. Another thing we would like to handle in this design is heterogeneous device-to-device links. In particular, we would like the ability to work with Bluetooth as well as Wi-Fi direct links. We also want our protocol to be free of sustained loops and handle delay-tolerant networking. In other words, be able to handle disruptions and delays in the delivery of packets. It should also be able to handle failures and resurrections of nodes and should be able to scale up to hundreds of nodes. The key goal in our design is to minimize the overall overhead of routing the data. We aim to achieve this by implementing a nearly unicast forwarding as part of our routing design instead of epidemic routing, which is the typical protocol used for delay-tolerant networks. We show in this slide the list of control messages we have designed for our protocol. In order to handle the connection-oriented link establishment and handling, we are using SYN and SYNAC as well as FIN and FINAC messages. When a router wants to establish a connection with another router, it sends a SYN message through the TCP-like link provided to us by the underlying link layer, and the other router replies with a SYNAC message and completes the setup of the new connection between the two routers. The cost information is also exchanged during these SYN and SYNAC messages. FIN and FINAC messages are exchanged similarly between the two connected routers in order to break down the connection between them. Each connection between two routers is maintained by regularly sending hello messages. The update message includes the distance vector updates that are exchanged between routers in order to find the shortest paths to reach each destination. Let's go through some examples of how these control messages are used in our protocol. The first example illustrates a connection setup between two nodes A and B. Node A initiates a connection request at the cost of 1 to B by sending a SYN message. Node B in this case agrees to the connection request by responding with a SYNAC message to node A and confirming the connection cost of 1. The second example illustrates how neighbors convey updates in their own distance vector table to each other. In this case, node B establishes a new connection with node C at the cost of 2. Once the connection has been established, node B generates 2 update messages to its neighbors A and C respectively. It informs node A that it can reach node C at the cost of 2, and similarly it informs node C that it can reach node A at the cost of 1. Nodes A and C append their distance vector tables with entries for reaching each other through node B. In addition to the control messages, we have 2 types of data messages. Data payload messages carry raw data, while data summary messages contain only the digests or metadata of the data payload messages to facilitate selective forwarding. In this example, on establishing a connection with node A, the patrol car sends node A a data summary message comprising of digests for packets destined to node B and node C. First, after the patrol car encounters node A conveys to the patrol car that it can reach B and C. Then, the patrol car sends the digests D1 and D6 only in its data summary message, since the messages 1 and 6 are destined to B and C, while other messages in its buffer are destined to elsewhere, not this shelter. On receiving the data summary, node A compares the digests D1 and D6 with its own message buffer. In this case, since node A does not have both messages, it requests both from the patrol car. Then, finally, the patrol car sends the messages 1 and 6 to node A. A key difference in our design from conventional distance vector routing is that we maintain 2 types of distance vectors which are differentiated by a binary state variable, 1 for active and 0 for inactive. This novel handling of the state also names our routing protocol, binary state distance vector routing. In our design, active distance vector entries are those that comprise of present connections that are still active. Conversely, inactive distance vector entries are made up of connections that were active at some point in the past, but in the present have become inactive. Both types of entries are used in constructing the forwarding table for the data plane, which we will explain next. In this example, the connection between node B and node C became inactive, which could be due to failures or disconnections. Therefore, the state of all distance vector entries that made use of this connection was updated from active to inactive. A major complication, as well as novelty, is how to calculate paths given these types of distance vector entries. Since we may have multiple paths available for reaching the same destination as active or inactive, there is a need to assign priorities between them. For instance, a new distance vector entry coming from an update message may be active while our current entry for the same destination is inactive, or vice versa. Our current design follows the following precedence rules. First, if both the present as well as the new distance vector entries are active, we simply choose the path with minimum cost by following the traditional Bellman-Fort approach. Likewise, if they are both inactive, we do the same. In case our current distance vector entry is for an inactive path, and we have the option of using a newly available active path, we will choose the active path if and only if it has a cost below infinity. This is needed because such active paths with infinity cost may be advertised by neighbors applying poisoned reverse, which is a technique used in traditional distance vector routing to avoid the well-known count-to-infinity problem. Otherwise, an active path should always have a priority over an inactive path, as it indicates a path that is readily available without any disconnections on the way. The final case is that our current distance vector entry is for an active path, and we just heard about an option of using an inactive path. In that case, we choose the new inactive path in 2 situations. An obvious case is that the current active path has a cost of infinity, while the new inactive path has a limited cost. We should choose the inactive path, as it does provide some chance of reaching the destination. In the second case, if the new inactive path is on the existing primary path towards the destination, this means The existing primary path has now failed or disconnected, and now we should be invalidating all the alternative paths towards this destination to make sure that any prior active knowledge or state which may cause fake active paths is reset. This resetting triggers the path towards this destination to be recalculated, which may result in a new shortest inactive or active path after convergence. The data packet handler component of our protocol works with the data summary and the data payload messages we described earlier. Each chunk of data in a node's message buffer can be in one of the three states: not forwarded, inactive forwarded, or active forwarded, based on the path they may have been forwarded to. Whenever a node receives a data payload message, it can do one of two things. If the data message is destined to itself, then it just needs to deliver it to the application layer and removes that message from its buffer. However, if the data message is not destined to the node, it keeps the message in its buffer marked as not forwarded until it encounters the destination for that packet or a neighbor that can reach that destination. After forwarding a data payload message, the node marks that data message in its buffer with either active forwarded or inactive forwarded flag, depending on the binary state of the forwarding table entry corresponding to that path towards its destination. This flag allows the node to try forwarding the data message again if it was inactive forwarded, and this helps us increase the possibility of delivering the data message to its destination. In the current design, we only re-forward such inactive forwarded messages if we find an active path towards its destination. Note that in a way similar to traditional epidemic routing, it is possible to make multiple inactive forwarding of the same data message, but that increases the cost of forwarding the message towards its destination. By adding more inactive forwarding possibilities, our design can be tuned for a more epidemic-style routing. We would like to show a glimpse of how the binary state distance vector routing works. Let's go back to the network setting where our patrol car travels from the command center to a nearby shelter and back. On arriving at the shelter during encounter 1, let's say that it receives data message 8 from node D to relay it back to node B in the command center. In the following slide, we will look at the distance vector table during encounter 2, when the patrol car arrives back at the command center and connects with node A. We can see that when patrol car arrives back at the command center, its distance vector table contains inactive path entries for reaching nodes D, E, and F, which are located back at the shelter. This information is shared with its immediate neighbor A when the connection with it is established. Node A updates its distance vector table by following our precedence rules and installs several inactive paths towards the shelter. Node A then propagates these inactive paths to node B, and B propagates them to node C. The inactive paths could be used by the nodes at the center for sending data messages towards the shelter now. Likewise, after meeting node A, patrol realizes the availability of an active path towards B with a cost of 12. It checks its message buffer and finds a not forwarded message towards B, which is the message 8. Then the patrol forwards the message 8 to B via node A. We have implemented the current design we have presented so far and are currently working on carrying out simulation experiments to evaluate its performance. We will be demonstrating the current implementation during the demo session. However, the current design can be subject to more improvements. The FIFO drop tail buffering rule on data messages can be enhanced further with the use of priority queues based on forming precedence rules on the 3 data message states in the protocol, that is, not forwarded, inactive forwarded, and active forwarded. The unique router IDs can be divided into groups for multiple shelters and command centers to allow aggregation of distance vector and forwarding tables. Also, we can include probabilistic routing of packets instead of traditional shortest path to improve latency. Finally, game theoretic incentive mechanisms can be included on top of the routing protocol in order to optimize the forwarding of packets.
Distributed computing can be crucial in first responder and public safety communication systems when there is little or no infrastructure support. For example, a map of disaster area may need to be created, which is usually computationally intensive, so distributed computing is crucial. Our approach to this problem is to divide a computationally intensive task into small subtasks and offload each subtask to multiple first responder civilian devices after coding to improve resiliency of the system. The challenge in this context is the heterogeneous nature of the first responder civilian devices. These devices may have different and time-varying computing power and energy resources. They may be mobile. We should also consider security and privacy concerns. Now the question is, how coding helps computation? Let us consider this canonical example. Our goal is to calculate matrix multiplication, YAX, at the master device. There are 3 worker devices. The master device divides the matrix A row-wise to smaller matrices A1 and A2. Smaller matrices are encoded using a 3x2 MDS code to give B1 A1, B2 A2, and B3 A1 plus A2. B1, B2, and B3 are transmitted to different workers. X is transmitted to all workers. When the master device receives 2 calculations out of 3, it can decode AX calculation. This means that one of the workers and its computation behaves as a joker in this setup. So if a worker ends up struggling, delayed, or unresponsive, it is still fine. We can decode the matrix multiplication. In this setup, if workers corrupt their data and calculations, that is, if Byzantine attacks occur, the master can only obtain a wrong value of AX. Therefore, it is crucial to develop a secure coded computation mechanism for edge devices against Byzantine attacks. Our solution to this problem is secure coded cooperative computation. Y tilde is the computed data that master receives from worker I. The master device checks the integrity of Y tilde by calculating hash functions H Y tilde, using computed values received from workers, and H BIX using local values at the master device. If these 2 hash values are not the same, the master concludes that the computed value is incorrupted. Otherwise, it is declared as safe. Hash functions are good, but they introduce high computational overhead and should work with coding because coding is the focus of our work. So our goal in this work is to use lightweight hash functions for coded computation. In our work, we consider master-worker setup. The computationally intensive task is the calculation of matrix multiplication at the master device. Matrix A is divided into R submatrices and they are coded with fountain codes. The workers incur random delays while executing tasks. One or more workers can corrupt tasks that are assigned to them. We consider collusion-resistant and homomorphic hash function. There is a trade-off between complexity and better approximation of A, which is the value that we would like to calculate its hash. We exploit this trade-off in the context of coded computation. We basically calculate alpha n using data received from worker n and beta n using local data at the master device. We prove that if worker n does not corrupt packets, then alpha n is equal to beta n. The other side of this argument, that is, if alpha n is equal to beta n, showing not corrupted data, depends on how CI values are selected. In fact, when CI values are selected from a set of 1 and minus 1, we have lightweight integrity check function, or LW function, while we have heavyweight integrity check function, or HW function, when CI is selected from a finite field FQ. We calculated probability of attack detection and computational complexity of these functions, and observed that when FQ increases, attack detection probability increases, but computational complexity also increases. Yet, it is smaller than the computational complexity of original matrix multiplication, where the master device makes all the calculations without offloading to workers. We consider the scenario that LW function is applied log Q times to the same data but different CI selections, which we call log Q round LW. We characterize the trade-off between log Q round LW function and HW function. Using this trade-off, we designed our SC3 algorithm. Our SC3 algorithm consists of two phases, phase 1 and phase 2. It applies phase 1 and phase 2 on the received packets from worker N periodically. The goal of phase 1 is to detect attacks with many corrupted packets and discard all these packets. Phase 1 uses LW function, and if attack is detected, all the packets coming from worker N is discarded. The goal of phase 2 is efficient attack recovery. Phase 2 either uses log Q round LW or HW functions, depending on which one has lower complexity. If an attack is detected, a binary search algorithm is used to identify corrupted packets. Only the corrupted packets coming from worker N are discarded. The rest of the packets are used. The logic behind this is that the attacks that are not detected in phase 1 are those with small number of corrupted packets. Therefore, the rest of the packets can be recovered and used. And also, since the number of corrupted packets is small, using binary search algorithm to identify them is computationally efficient. We simulated SC3 and compared it with HW-only function for 150 workers. The results show the task completion delay versus the number of malicious workers and probability of packet corruption. As seen, SC3 significantly improves the task completion delay as compared to HW only. The second project we worked on is network coding over intermittently connected D2D links with infrastructure support. Consider a scenario where a group of first responder devices is in the same geographical area, not necessarily in the same transmission range. A common content, for example crucial voice instructions, can be broadcast over infrastructure-based links. Device-to-device connections and network coding improves reliability in the setup. We consider that the system consists of two phases. In the first phase, common content is broadcast from the source. In the second phase, first responder devices cooperate using D2D connections to recover the missing content at each device. Each device in the second phase can receive recovery packets via cellular or D2D connections. These transmissions can occur simultaneously as cellular and D2D links can use different parts of the spectrum. We use network coding in this setup to recover missing packets as quickly as possible. The crucial question in this context is which network-coded packets should be transmitted over each interface. Let us consider a motivating example for using network coding and D2D links for recovering missing packets. In the first phase, all packets are broadcast via cellular links. After this phase, each device has received some packets and missed some other packets. For example, device 1 has the packets in its hash set H1, which are packets P2 and P3. Device 1 still wants to receive packets in its one set W1, which are P1 and P4. Let us assume that coded packet P2 plus P4 is broadcast via cellular links to all devices. Device 2 broadcasts P1 plus P3 to device 1 and device 3. Note that the other devices are not in the same transmission range of device 2. And device 5 transmits P3. Thanks to these network-coded packet transmissions, all missing packets are recovered. For example, after P2 plus P4 is transmitted, device 2 recovers P2. After P1 plus P3 is transmitted, device 1 recovers P1. Similarly, when device 5 transmits P3, it is recovered at device 4. Still, the question we asked earlier remains that which packet should be transmitted over each interface and from each device. Due to time limitations, I will not be able to go into details, but our approach is to convert the problem to a two-layer connected graph, one for cellular, one for D2D. Maximum independent set gives packets and network costs to be transmitted for cellular and D2D. So this is the optimal solution that we find. We also designed an efficient heuristic to determine which packets should be transmitted over each interface. These are some simulation results of our optimal solution and proposed heuristic as compared to the baseline NCMI instant. We present average completion time versus number of D2D nodes and number of packets. As seen, proposed heuristic is very close to the optimal solution and significantly improves the average completion time as compared to NCMI instant. To conclude, we designed mechanisms for secure coded computation and network coding over intermittently connected D2D links. Our future work includes the development of coding techniques to improve the reliability of our architectures, specifically focusing on the scenario for communication and computation among nodes that have dynamic heterogeneous capabilities, including varying number of communication interfaces, battery levels, and computation powers.
Now, we'd like to report the status of implementation and integration of our designs in the ReDiCom demo. In last year's PSCR conference, we presented an integrated version of the messaging and cooperative computing apps from 2018 with our PubSub over graph-based namespace on device-to-device links. It used a layered design so that each layer can provide different abstractions to the upper layer, while at the same time different protocols or modules can coexist in the same layer to satisfy different requirements. From bottom up, we had the link layer that provides connectivity and reachability of physical nodes using the Bluetooth, legacy Wi-Fi, and Wi-Fi direct connections. It monitors the connectivity status by sending keep alive messages and performs packet fragmentation and aggregation in data delivery. The network layer provides robust content delivery over the virtual links via gossiping and static routing protocols. The naming layer performs namespace management and PubSub message delivery over graph-based namespace. In the application layer, we hosted two applications, namely the messaging app and the coded computation app. In the messaging app, we allowed an incident commander to dynamically instantiate a template when an incident happens. This step creates a set of names and corresponding relationships in our namespace. Each name represents a role to be acted by one or several first responders. These names are shown in the blue color. The incident commander can then request the dispatcher to send some units for each role that he needs. The dispatcher sees a view of available units and can dispatch first responders with simple drag and drop. We use a yellow color for representing the organizations and the first responders. The updates from the dispatcher are shown on the screen of the incident commander and the first responders involved. The incident commander and the first responders can now use the namespace to send messages to different groups of people at different granularity. For example, a message to Rescue Squad 1 will reach 3 first responders in a group, while a message to Reach Crest will reach everyone dispatched for this incident. In short, the messages will be propagated according to the arrows in the namespace to all the subscribers below. In our demo, we enable both text messages and voice messages similar to push-to-talk that is widely used by first responders. A benefit with the role-based communication is that the communication parties do not have to keep track of which units are currently in a particular role. Personnel changes during shift changes can be performed seamlessly. With the help of the D2D communications provided in the link layer and the gossip protocol in the network layer, we enable the apps to operate in the infrastructureless environments, for example, a shelter. When the shelter is not far from the coordination center or one of the devices can reach the internet via satellite or LTE, this device can act as a relay and all the messages can be delivered immediately. If the shelter is not reachable, we can have a data mule, for example the patrol car in this demo, to carry the messages and the updates to the namespace back and forth. The Coded Computation app allows a first responder to find a particular person in a set of images. With the help from the other devices, this process can be accelerated. This app takes advantage of the device-to-device communication in the link layer and the static routing protocol in the network layer. It also uses the namespace to detect available helper devices. This app can also distribute the workload dynamically to nearby helpers according to their processing power and link quality. Building on the basic functionalities in last year's version, we improved the design and implemented a version with better lower layer design while retaining the user experience. We implemented a modularized design similar to the design adopted in 5G access networks. In this design, each layer becomes an abstraction or code skeleton that provides standard interfaces to upper layer modules. These interfaces include retrieving current status, sending data, and registering handlers when a piece of data is received. We then implement different modules that instantiate these functions of the layer skeleton. With this mechanism, we only need to register the modules that are needed on each device. For example, on a device without Bluetooth connectivity, we can easily omit the functionality by removing the registration of the Bluetooth module in the link layer. This also allows us to design different modules for the demo this year without the need to worry about interoperation among different components. In the new design, we placed lower layer functions on separate threads instead of the UI thread to ensure the responsiveness of the application. We used RCU, read, copy, update, and event queues to avoid deadlock issues when different modules are working in different threads. We also built a new library for packet processing that helps to avoid copying memory when the packet is passed between different layers. To improve the stability, we redesigned an Android version of the UI for the dispatcher and incident commander and use WebView to host the graph. This eliminates the possible disconnection of the web sockets and allows us to use Bluetooth and Wi-Fi direct connections to connect directly with the other devices. The new design improved the stability dramatically. We demonstrated our new design in conferences like ICNP, SmartCom, and other occasions, and received many positive feedbacks from both the academia and the industry. While we keep improving the implementation of ReDiCom, we participated in Contest 2 of Tech to Protect Challenge with some of our designs favored by first responders when we showed the ReDiCom demo in the past. The contest required us to provide an efficient push-to-talk tool on top of the Mission Critical Open Platform, or MCOP. For the project, we addressed 3 issues with existing MCPTT systems. The first issue is that messages cannot be stored or replayed. When the receiver isn't able to hear it clearly, he is forced to ask the sender to repeat. This not only wastes communication channel resources, but also the precious time of the first responders. The second is, when a first responder needs to focus on some task and come back to the interaction later, he cannot pause the message and play them when he is ready to listen. The third issue is the difficulty in serializing speech, especially on a connection with long delay, for example a satellite link. First responders end up wasting a lot of time waiting for the floor or just talk over each other. To address these issues, we substantially enhanced the MCOP with our innovations. First, our application stores the messages that are received. This allows the user to replay a message if he could not hear it clearly, or pause the playout when he needs to focus. Second, we allow users to push and talk whenever they want to. Our application monitors the availability of the channel and sends the user's messages when it can acquire the floor. The application was awarded the first prize overall and the first prize in Contest 2 in the in-person contest in New York site. We got a chance to demonstrate both our applications and have first responders use it in the Disaster City exercise at the Texas A&M University in January. They liked our designs on the dynamic group management, fine-grained message delivery, and added features for push-to-talk. They also favored our consideration of the support for the infrastructureless environment using device-to-device communication. At the same time, they recommended us to add the function to allow first responders to send emergency messages and give the messages a higher priority. We have now included the feature in our applications. They also desired a map function that would allow them to distribute tasks and communicate based on the geolocation and add markers to different locations while performing search and rescue. We enhanced our push-to-talk app based on the feedback we got and participated in the Tech to Protect online contest. The enhancements include the capability to send text messages to reduce the cost in the comment channel, cloud-based speech-to-text and text-to-speech capabilities, emergency calls and call prioritization, a group management tool which is a simplified version of that in ReDiCom, and a map which shows the location of the units and aid the dispatching process. The enhanced application got the Superior Award, which is the best in Contest 2. Some enhancements are brought back to our ReDiCom app with further improvements in both functionality and efficiency. We'll be demonstrating the application enhancements in the demo section for this year. The first enhancement is a map tool in the application layer. We have added a location placeholder in each template. The location-based names are shown in green in the namespace. When instantiating a template, we also add the location-based placeholder to the namespace. In the new map view, we allow the incident commander to create and edit a hierarchy of areas. The application modifies the namespace according to the map hierarchy the commander created. The commander can either directly mobilize units available for the incident or request the dispatcher for new units just like the messaging app. When mobilized to an area, the unit receives a message carrying the area name. He can double-click the area name and enter the map view with the area highlighted and centered. The first responder can then add and modify markers in this area. We allow the unit to create markers in different categories represented in different colors and add a short description for each marker. These markers will be synchronized with other units in the same and all the ancestor areas. This includes the incident commander who subscribes to the top level area. The incident commander can click on a marker to see the detailed information, which includes the location, the type of the marker, the time and unit that performed the last update, and the latest description. He can also filter the markers based on the categories on top right. Other than the markers, the first responders can also use the location-based names to communicate. A message sent to an area, for example East, will be delivered to all the units in this area, including the units dispatched to the sub-areas like East-North, East-Mid, and East-South. Please note that we have two sets of propagation requirements in this case. The markers follow a topic hierarchy. For example, when a marker is added in area East-North, it will be propagated to subscribers of East-North, its parent area East, and its ancestor area Jersey City. In contrast, the message delivery follows the recipient hierarchy. When the message is sent to area East, it will reach all the subscribers of East and its child area East-North, East-Mid, and East-South. With the namespace using directed graph, we're able to unify both the requirements in the same namespace and have a single forwarding rule, propagate the messages along the direction of links. The map tool can also be used in infrastructureless environments. When first responders encounter each other, they would exchange the markers. The information can also be brought back to the coordination center via data mules like patrol cars. In the network layer, our consensus protocol helps the application to understand the order of the markers and to determine the latest state for each marker. It maximizes the delivery with ordering at relatively low cost. To allow the first responders to be eyes-free even when they're receiving text messages, we add the text-to-speech capability. Unlike a cloud-based approach, we adopt a solution that can be performed locally on the devices. Similar to face recognition app, we use helper devices to accelerate the computation and dramatically reduce the time needed to synthesize the voice. In the demo, we'll also show the dynamic routing protocol, which can adapt to frequent topology changes in the device-to-device communication. If you're interested in any component mentioned above, please refer to our demo video for more information. These components are now implemented separately due to the current situation. As future work, We'll integrate them into our main Android codebase and show a unified application in the next year. The modularized design would minimize the effort needed in integration. We'll also use the opportunity of Tech to Protect to push the applications into the field and request more first responders try our app in their exercises and regular work. We'll keep improving the applications based on their feedback. Thank you very much for your attention. In case you have any questions, please do not hesitate to contact us. We have listed our emails at the bottom of the slide.